latest ones?
Yes, latest ones.
Thank you, Namita, for looking after that. Let me share.
मुझे भी
YouTube लिंक
मुझे भी भेज।
WhatsApp
व्हाट्सएप तुम्हारा चलता नहीं आप जल्दी से।
नहीं इसमें मेरे फोन में ले लिया।
ठीक।
So just confirming, you can see my screen?
Yes.
Yeah.
Nicely. Yes. All good.
Okay. Good morning, everyone. Day 2 or module 2. So in module 1, we introduced you to generative AI. We explained the difference between traditional AI and the generative AI that is beyond traditional machine learning. And a lot of success behind Gen AI is because of advancements in language model called as large language model. So in today's module, we are going to look at language models and large language models. In here, people who have been doing research in the area of NLP, they may find the early slides are basic and introducing the field, but I'm assuming that not everyone is aware of language modeling. They may be aware of text mining, just a bag of words, but not really the concept behind these language models. So today's module then focuses on language modeling to start with, and then we'll move on to large language models. So as yesterday, the disclaimer, and I hope that the participants would use the material in most academic integrity and conscious way. So as I said, we are going to start with language modeling problem. And then we are, the most importantly, how do we learn a language model? And you would notice that language model is nothing but probability, like discussed in module 1. Today's large language models, actually, they calculated probabilities. And probability is not just on a small amount of documents, but just very large amount of repositories. So we are going to look at what is really the process of estimating probability. And a majority of time, these language models do learn about next word predictions. But we do go beyond next word predictions that allow these models to be used for classification, regression, generation. So that relates to today's workshop session that Deepak Unyal is going to run and lead. And as introduced again in module 1, the success behind LLMs is transformer models. So we are going to look at various architecture of these transformer models. And as I mentioned in module 1, our aim is not to introduce you to the basics of deep learning models. We assume that you already have the knowledge about deep learning models. So our objective is to quickly recap those models and then focus on that how these models are used in language modeling problems. So again, I'm not going to go much more detail into the transformer, what it is, but just quickly recapping why it is suitable for language modeling problem. And once we know the language modeling, establish the basics of it, we are going to move on to large language models. We are going to introduce to BERT, that is encoder-based language model, and then we will see GPT and Llama, those are decoder-based language model. And in the workshop session, Deepak is going to go into much more detail about the bird-based models and use them for classification purpose. As I was mentioning in module 1, when you speak to industry participants, they are still using bird-based model for most of the language modeling concepts because they are most resource efficient and do not compromise on accuracy, best for fine tuning. And that brings us to the next topic of today's module, that is fine tuning. So LLMs are, they are monolithic thing, and not all of us can use those large models for our purposes, but rather we can use them by fine-tuning. So we are going to explain you the process of fine-tuning them, and then finally I'll finish off with the evolution of them. How, just recapping from early on developments of language model, that was the statistical modeling that was well established until these language models come, and then the language model. So you will see some of the materials in the lecture notes would be highly related to the tutorial sessions. We cannot cover all parts that we cover in the theory part. So we pick one part of these lecture materials and then focus on them in the workshop or tutorial session. So today, Deepak is going to show you how these language models, mostly the bird-based and some other models, use in for classification tasks. And as I said, that in early modules, we focus on the classification task for you to understand the concept. And then later on, we show you some advanced cases of these LLMs and Gen AI techniques. Okay, so language model, once again, it's not new. We are using them for many, many years, like information retrieval and information extraction. They are very established field. Information retrieval and those fields have been around for the last 30 years. So they are all based on statistical probabilities. So for example, when we type in our phone or computers, I'll meet you at so the most probable word would appear after these phrase would appear. In the same way, Google, when you are typing the query, what is the, and then you can see many suggestions. So they are based on what are the phrases appear in the corpus that the search engine uses based on their frequency, and also relate it to their query logs, that when people uses these phrases, what are the other words or phrases appear after that. So it's all about frequency from your corpus on which the information retrieval or machine learning or Gen AI systems have been built, and the logs, how people are interacting. So when we use these two material intelligently, we can do so much more of these generation. So how it is eventuated, you have a very, very large corpus. This definition of large is always subjective. It could be something that is does not fit beyond your laptop, or in a large language model case, it is trillions of billions of tokens, or it could be just the Wikipedia documents, or it could be just the web scrap. So essentially, you build a language model based on this corpus, and when you interact with this, like for example, the best recipe for, and you write BI, again, it would get the most probable words that appear with this one. So you can already get the feeling that the word that I'm using very often right now is probability, and the most probable words. So you can see that language modeling is all about probabilities. So let's see how these probabilities are calculated and in more detail. And these days now, language models are trending because of these intelligent conversation agents like ChatGPT, where you don't just type one word, you can type many instructions in the form of prompt. And so you can see the information retrieval like Google search engine and all those things. We call them just the global information retrieval. You type the query and you get the entire documents. You don't get the most precise answer. On the other hand, you have question answering systems or some of the search engines, those are based on the question answer. So they would give you the precise answer. That precise answer, we call it focused information retrieval. So focused retrieval gives you the precise answer based on the question you typed. So large language model is towards the focused retrieval, but it is not just based on what it is repository. So before large language model or before Gen I, the systems would only extract the information that exists in corpus. They would not make up the answer. If it does not exist, they would not answer. But the language models, those are based on Gen I techniques, they would answer and they would do some intelligent processing like summarizing, fitting to the best answer, and to a certain extent, they would create the answer. And sometimes that's why we result in hallucination, and we would see into more. But at the same time, they give you much more explainability. So for example, like you can ask, why do you think it is a good movie? So it would have the capability of extract the information, summarize the information, and then resonate the information and present in the most intuitive way. So users can relate to it. Today we are going to see that how these kind of question answering is achieved by certain kind of training. So those trainings are very important for LLM to provide us those answers. So not just the answers that exist, but then make up a nice story based on those information provided, but also present in the manner that human align with or humans resonate with. So now let's see how these language modeling problem works. So for example, when we give this phrase, I want to, so what system would do, this given a sequence of words, and it takes that sequence of words, and you can think about it's a context. So we are giving, so we have got subsystem that have some historical data, and it has got a lot of information about the language representation. So for example, Wikipedia, some story data, web scraping, and so on. So they would already have many corpus, each corpus organized in the form of sentences. So how you go, it would take the current query words that user has written as a sequence, and in a language modeling problem context, we call it context. So now its task is to predict what comes next. So what it does, it would go into the corpus and would see what are the next word, if it's a next word prediction problem, and that's what most of the LLMs would do. And it would see what are the next words based on the frequency that appear in the corpus. So something like that. It will pick shovel, play, swim, eat. So now how you got multiple sentences. So rather than just I want to, now we got I want to shovel. So this word then would become the sequence of words. So this path would become one sequence, this part would one sequence. So now you have got kind of like multiple parallel problems. So that's why in old statistical timings, we were limited by their capabilities and their resources, because all of the sudden, once you have got this one sequence, it became 4 sequences for this example, and we now have to process them. So, and the process keeps going on. The next iteration would have, I want to shovel snow, I want to play tennis, I want to play video. So essentially what language model is doing, it is doing next sentence prediction in recurrent way. So recurrent word came in. So now you are reiterating the same process again and again. So for example, you are now calculating the probability of I want to shovel snow. And then the systems during the training time, when, let's say, if you write, how are you this evening? So the language model would go and would find out what are the sequences that appear with this one. So for example, how are you this evening? One response is, has your house ever been burgled? Or, fine, thanks, how about you? So the system would find that the probability of this first phrase following the query is very, very low, whereas the probability of the this second sequence is much, much higher. And so the process is that you do ranking. So essentially what we are doing, we are counting the probability and then we are ranking. So for example, if we have a sentence like Jane went to the store, and we know in the corpus, it would appear in multi ways, or that's like if we are doing in terms of machine translation or some other kind of translation, then we have many variations of that. So what it would do, for each sentence, you will have variations, but you are doing the same thing. How probable is a piece of text? So now you can see either you are learning, like whatever it is, you are learning the probability of that sequence. How, so when they are answering, they are assessing the probability of the answer that they are going to answer, or they are going to add on, depending upon what your problem is. If it's a question and answer, they would get this phrase, and then they would see how is the probability. So these are the most probable answers, and then rank them. The one that is the best would be displayed. If it's just the next word, like machine translation or token prediction or labeling, then they would just do what is the next answer, something like that. But the basic behind this is calculating the probability on the sequence of text. So in LLM language, we call it tokens. So we have got a number of tokens. The problem could be the next token prediction, or the sequence of tokens, that is the answer prediction. Or it could be that given the token, sentiment prediction, whether is it a positive, negative, or neutral. So many tasks, but the fundamental is probability calculation. So something like that. One sentence, Jane went to the store, score it, store to Jane went there, something like that. So we know one would be high, another would be low. So essentially, it is same as like how in neural network training or deep learning, we feed one sentence, we get the answer, and if the loss function or the RMSE value is very large, it's not good, it would adjust. So in pre-deep learning era, we are just calculating the probability, not much of generalization happening, but post deep learning era, we start to get feed them back and calculate it. So we are now adding the generalizable capability. So for something like that, we feed the color of the sky is, feed to the language model, it answers blue, and it gives 91%. And we will soon see the concept of color, how it gets it. But that's how it happens. It predicts the next word, and if the probability is very high, it would go back, adjust the weights. But let's say the color of the sky is something is saying grass or tree or some other random word redundant, then the probability would be very small. RMSE loss would be very higher, so the weight adjustment do not happen. The same way we do when it's a generation task, we get the probability and the sentence with the higher the probability becomes the answer for that. So far what we are seeing, we call it unconditioned prediction. So predict the probability of a single variable or a single sequence of variables. But we are not really conditioning. So this is kind of unsupervised learning. And that is the success behind language models. We don't really have to worry about the annotation. Let's calculate the probability of the given data that exist in based on the information that exists in the corpus. The second one is condition prediction. And this condition prediction is supervised learning. This one helps us to, so let's say we start with unsupervised training, and then we have a small level of annotated data. So now we would have that small annotated data. We would leverage unlabeled data and make the system to have better accuracy. And the deep learning era has allowed us to do these conditioned probability and unconditioned probability in collaboration. And that's why we have got such a large language models, and those have quite high accuracy because they have got unsupervised learning phase that is mostly pre-training, and then they would have another phase where they would have this condition prediction based on human feedback, even based on their own answers or based on human feedback. But in this one, what they do, they predict the probability of an output variable given an input. So this condition prediction is highly useful to use these language model, not just for generation tasks, but for many more tasks, and make them monolithic systems. So this allows LM processing, and this is not just post deep learning era. They were already existing, and IR or statistical researchers were using this kind of concepts. But of course, they were constrained by resources, they were constrained by the training algorithms, and they were dealing with the small data sets. So in a question answer system, you get multiple answers, you score and get the best one, generate a continuation of a question prompt. If you want to classify the text, you score the text conditioned on a label, and then generate a label given a classification prompt. So you can see during training, the system is trained to do the scoring, and during inferencing, the system is trained to generate whatever answer we want. If we are after correct grammar, like Grammarly and many systems, they were again using score each word and replace low scoring ones with the high scoring ones. So that's where we get like how these systems. So most of the NLP systems already have been utilizing this language model processing, may not have been at scale, and that's where their limitations were. So let's quickly look at the mathematical framework. I have avoided lots of mathematical formulation, but I'm still introducing some of it because any machine learning course can't be completely without a mathematical formulation there. So for example, here we want to predict this text. So text would be represented as sequence of symbols. So in pre-deep learning, they were bag of words. You would do a lot of pre-processing, remove stop word removal, do stemming, and then just get the words. You would remove any conjunction words, any common words, and so on. So you would have just the bag of words, the keywords. Whereas in post-deep learning era, we take the whole sentence as a sequence. So like, I am teaching this course. My name is Richi Nayak. So nothing would be filtered. Every word would be used as token. Deepak is going to give you some more examples and details in terms of how we do the processing for language models during the workshop session. So mathematically, we express that given this input, calculate the probability of this sequence. If we apply a Bayes rules, and I'll explain you very quickly what is that Bayes rule. So essentially, this part, that is the chain of, the sequence, can be written as probability of chains of sequence. So how it can be written, that give me the probability of first token, give me the probability of second token given the first token, give me the probability of third token given the prior sequence of tokens, and the process keeps going on. And this can be now expressed with this equation, where for any prior sequence, and we call it chain rule, predict the next token or next word. So this makes this language model workable and decomposable and solvable by any intelligent system. This reduces the language model problem to modeling the probability of next word, given the history of preceding words. So now we have formulate the language representation as a language modeling problem and make it solvable through any mathematical system there. So essentially, we are doing predict the prior sequence to the tech one. So an example would be if we have got a sentence like the students open there. So now we find many next token words probability, and this would be represented like that. So and that's why it is important that what is your corpus. So usually we use the terminology vocabulary. So whatever is your, so think about English language. If we are dealing with English language, essentially your vocabulary is, if you are using Wikipedia, almost every token that exists in the English language. But that's how you get the probability distribution, and the system would go rank them and present them in the ranked order. So now, it just that, so how system process it, you have the students open, there. It's a recursive process, and at each next step, the process is becoming explosion. So there are many ways we control this explosion problem. One thing to note down in here is the system still does not know anything about grammar, how we do it. It is only a statistical probability system. So it would also produce very nonsensical word. So for example, like it might say the students opened their forms, or opened their, nothing is coming up, very redundant word, that would never happen. something like that, grammatical or not. And that's why you will see sometimes language models are producing very nonsensical results. They do not really understand the meaning in the way of understanding the meaning. But if you now relate, this is like what when we were kids, that's how we were taught, fill in the gaps. So that's where then we get this problem and we make these LLMs to learn these fill in the gaps. But now notice in here, there is no order. Anything can be missing there. And this is what we call mask token. And that is another success behind language model. So what language models would do, language model may not do it sequentially. It may just mask any order that the next word would come, and it would try to predict that. So it is very much like how we learn, no sequential process. But that's what researchers have done, try to incorporate this process. So what we are doing, like another example, we are doing this chain of probabilities with the Bayes rules, and this one is called conditional probability, that given the prior sequence, predict the next one. So like the cat sat on the mat, so we would do, and this order is an implicit order. It would learn by itself that this ordering is doing. And you can see it's a very rigorous process. GPT-3 models or any GPT family of models, they are still learning this way, next word prediction. But the only difference is it's implemented with 175 billion parameters model. So it is learning more and more of that probability. And that's why there is a good chance that the answer that we find would be correct. Okay, yeah. So now, okay, let's see. And as the module 1, please use your chat box to answer it. Why is the probability assigned to a sequence by a language model important in the NLP task? It determines the grammatical correctness of the sequence. It allows the model to rank sequences by how likely they are to occur. It ensures that only predefined are generated. So I can see many of you answering B, and that is the correct answer. So it, as I said, probability and ranking. That is the basic behind it. So now let's see how do we learn a language model, a little bit more into the detail and what are different models. So as we know, it is estimating the probability and then calculating the probabilities, and then this we call distribution. Then we find the distribution that maximizes the probability of the corpus to answer that. And this process is called maximum likelihood estimation, MLE problem. And this is what we solve with the optimizer. So any deep learning models and things, they would have this one. So a naive solution, how system works. Let's say you have n training instances, you have a number of sentences. Let's say x1 to xn is the sentence. So what you do, you go into the corpus and you count how many times this sentence appear within the corpus, and then you divide by the total number of sentences in the corpus. So n is the total number of sentences in the corpus, and you get the probability. This is giving you the probability of each sequences, but it is a deterministic process. There is no generalization happening. So what we do, we apply this Markov assumption. What we learned before, that the prediction of the following word depend on the preceding n minus words, what we have seen, n minus words predicting the next word. So for example, it's water is so transparent, the sequence, or sometimes just based on the word. So something like the predict the probability of its water is so transparent that next word by just sum of the word token. So we all know about Markov models based on these assumptions. So far, statistical researchers or IR researchers were using Markov model. So this is a stochastic model that predicts the probability of a sequence of events where the probability depends on the attend. So something like that. You have got a word or the token S. What is the probability of reoccurring this word again in the sentence, or what would be the following word? Would it be cloudy or would it be raining? So now you can see that it is able to learn the sequences, but you can see there would be the explosion learning that. So you need the model that has got the capability to learn this recurrence by parallel processing. So if we are just using simple Markov model, then we may be constrained by the parallel processing, and also it is going one step back. So this one, it's great to do the modeling sequences, but it struggle with long range dependencies. Pre-deep learning, people were using n-gram language model based on this Markov assumptions. So they are collecting statistics about different n-grams. So given the corpus, like Google search engine, whatever corpus they have, they would count the frequency of each word that appears in the corpus. So just to rephrase, we call it n-term, n-grams in general, but usually we start with unigram, where one word at a time. So let's say this is Big Data AI book. So you would have terms. This is, so each of the word that appears in the sentence is called unigram. If it's a bigram modeling, then you have got the window of length 2, and it is an overlapping window. So you would have this is big data, data AI book, and so on. If it's a trigram, then you have the window of length n, and this would be this is big data, and so on. So that's what n-gram language model. You count. So essentially what you count, you have the corpus, you count those unigram, each of the unigrams or each of the bigrams or each of the trigrams. So you have that frequency, and based on that frequency, you are counting this probability. So these systems, they would have all probability counted. So this is an example of trigram probability. So I'm not taking time, but I think this could be your homework, especially if you're not familiar with the area. Get a particular sentence and generate those probabilities, so that help you to understand how it works. So eventually, if we generalize this system, we get that the probability of each preceding sequence predicting the next word is the counting of the sequence divided by the count of total number of the sentences there. And this becomes our model, and this is called the probability model. So these models are very, very effective for small data sets. There is no space for error, because you are doing such a meticulous calculation where you are going unigram, bigram, trigram, but the as you say, if it's a unigram, length of 1, bigram, length of 2, and things. So it is not possible to do every possible length of window. So you are limited by the fixed length and then the probability. So if, let's say, your system is based on bigram, but your queries and answers asked are very large, you are adding a lot of randomness to your answer. Let's see this question. Take a pause. In a language model, the sum of probabilities assigned to all possible sequences must be equal to 1. So that is the basic concepts. Whatever we are doing, it's based on that the highest probability is 1, the sum, and then it goes less. So great work. So let's generalizing this to neural network language model. So essentially what a language model is also learning this function. This mathematical function is learned by the network of connection. So this function of theta, this is a differential function. So what it is doing, it is trying to learn this probability. So you have got, you feed this neural network model sentences. And what it is learning, this function of theta is the probability. And so it would, depending upon what your task is, it would try to learn the classification or generation or regression, whatever you are, or extraction, it would do. So let's see, just to give you a bit of the scalability concept. This is a network with trainable parameters. So we are calling W as the parameter, that is the connection weight that we would need to train. So such a small network with 5 input, 2 hidden layers, with 8 in first hidden and 4 in second hidden, and then 3 in output, you get 99 trend parameter. Now think about the scale of GPT-3, 175 billion parameter. Look at the size. So it may be about the size of your room that you are sitting currently. So we are learning more and more of this. With deep learning, it allows this self-supervised learning. So for example, we have got a large text corpus and we say the Trevi fountain is in the center of, so language model has learned a lot of probability distribution like this. Based on this answer, it would have Rome with 96% probability, and any other cities with very low probabilities. So as such, you can see there is no learning happening in the corpus, because this sentence Trevi fountain appears most of the time with Rome. So that's why, just based on the distribution probability, the language model has learned that the answer of this particular sentence would be corpus. So now you can realize that whatever system that you are using, it is subject to the training corpus. So that's why it becomes very important, whether you are doing pre-training or fine-tuning, that or even if you are doing domain adaptation, that you have some alignment. The answer or the inferencing task you are going to perform on the input there. So that was all about kind of like unconditioned prediction. We were doing to do the prediction task, next word prediction. Now look at the condition prediction. So now what we have input sequence X and some output sequence, and we are now trying to predict the next word in the output label. It could be just the single label problem or multi-label problem, or it could be translation problem. Now we have got a mathematical framework that we call autoregressive. So what we are doing, given input, we are trying to do this regression task, predicting the next word, but we do have given the probability of these output Y. So we have got this X and Y, and we are trying to predict this Y. So it's a typical regression task, but having the setting in a language modeling task. So now it allows us to do classification, sequence labeling like NER, named entity recognition, or MT, machine translation problem. So let's see how it can do. Given an input X, the basic system would extract features or embeddings and would try to predict Y. If the prediction is just a single label like positive, negative, neutral, it's a sentiment classification problem. If it's any classification like if this story belongs to comedy or it belongs to drama, multi-label, then it's a classification. Or this is NER, named entity recognition, that given a sentence, can we identify that I is a pronoun, like is a verb, and peaches is a noun. So the same model, same mathematical framework is allowing us to do multiple tasks. Now let's see how deep learning is enabling that. So the first most successful models in deep learning were recurrent neural networks. And recurrent neural network, you can think about it that we were trying to learn the probability of the prior sequence, and RNN have been naturally made for that. So this is your input embedding going to first RNN unit or bi-RNN unit, and then it is fed to the next unit. So it's a very much automatically conditioning of encoding of the history. Then if you are using LSTM, that is the advanced version of RNN, you have got this long-term, short-term memory there. Then CNN models were also used. So recurrence made for that. But we all know that CNN have been meant for image recognition part, because they learn the image tokens and things, but they are very good for language modeling as well, because they learn the local context. So given a sentence, it learns the local context that noun is followed by verb, verb is then pronouns, and so on. And the good thing about is that they like each input unit is fed to this CNN unit, and it is learning. So the earlier unit would learn the abstract information, and as we go forward, it would start learning the concrete information. And then we have attention-based model where condition representation on a weighted average of all tokens. So every token would be fed to every attention unit and do the multiplication to identify which particular token relate to what other token. So this one starts to learn the importance of the words in the sentence. So these were kind of the sequence models that really changed the language modeling era. Learning from the just the one word to sequence of words to prior sequence of words to all sequence of words to learning and to do the attention. And so that's how an example. And in the workshop, we use the RNN model in this particular way. So let's look at the first, that is my left top corner. So you have soft sample word, then you have got softmax function to generate the probability for that embedding. It is fed to RNN, so you got input word, then the embedding fed to RNN, or RNN generates the probability with the softmax, and then you have got sample word. But then each of them fed to the next word, and we would remember. And we usually have the CLS token to start with, and kind of thing. If it is for machine translation, you don't just have one sentence, you have one sentence and you have got the separator to show that this is input and this is output. So source and target. But it is done in the very similar way. You have got input embedding, it's a feeding back, and then what you learn from the input starts feeding to the target and you learn it. And if you are using for sequence classification, So the hidden state of the last word in the sequence is used as an input to a feed-forward network. And then softmax function, and you get the distribution probability, and you get the answer. So this is the most common way we use these deep learning model for classification purpose. So Deepak is going to show some traditional machine learning models and then move on to the LLM models. So just a recap of NLP systems, we can see given input, if the continuing text, it's a language modeling, a text in other language, it's a translation. If we are predicting label classification, language analysis, if it's a image to text, image captioning. So there are many now multimodal data, they would accept the image and input and then would produce text as an output. So like based on this information, we can create any language model. What we need a very large corpus. The current systems, they use Wikipedia books, Stack Overflow, Quora, public social media, GitHub, Reddit. So they have got all kind of information there. You learn the probability there, randomly truncate the parts off, calculate the probability of missing words. So we call it mask tokens kind of thing, and then have some kind of training that adjust at feedback to model. So it's unsupervised, but because it's a sequence, we know what is the next sequence, next word, and then repeat over the whole corpus. You got your own language model there. So that is the basic concept. And but now what has changed? The corpus have become very, very large, unimaginable size. So that's why we call them large now. And they are general purpose. We call them large. We have got petabyte of training data. We are using unsupervised, but at the same time, we have got large number of parameters. Like we saw an example of 99 parameters, but these large language model have got billions of parameters. We call them general purpose. As we saw, they can do classification, labeling, regression, whatever you name it. So for example, if I show you this example, when we have a dog, and you will see, I've got many examples of dog. I've got a dog at home as well. So you teach them many instructions like sit, down, stay, come, and run. You are not teaching just one instruction, many instructions. Now you have got guide dog encapsulating all those kind of instructions. So that's what large language models are. We are not just feeding one type of task, we are encapsulating multiple type of tasks. So the large language learns that. And how do we use it? We have got pre-trained and fine-tune, and we use it. So the building the language model is very computational expensive. Not everyone is involved, as we have seen some of it in module 1 as well. But the computationally inexpensive is fine-tuning. So that's what we will show you in today's workshop, that how do we fine-tune and use them for classification purpose. So how do LLMs work? They have, so essentially it's a statistical pattern recognition and prediction system, what we have seen. So far, the only difference is that we have got large number of tokens. We have got multiple windows recurring over sentence, paragraph, books. So for example, if we think about ChatGPT, the size is 4096 tokens, and Cloud 2, it's 100K tokens, quite big. So our window size is becoming larger and larger. And essentially, training is done on corpus, and then how do we inference? As we saw some example in module 1, prompt. So first, building the language model on corpus is training, and asking the model the question through prompt is using or testing or generalization. So this slide is very interesting. Based on, like, we have seen LLMs, we sometimes get confused that they are understanding the language or they have learned the meaning of the language. Of course, yes, they do understand the language, they do understand the meaning, but this is very different from the way we understand or we mean the language. So this apostrophe brackets are put there in purposely. They learn, they understand, but they are very different. So they are based on all statistical. Because of it can consist many data about the same concept. It learns through those statistical probability, but it does not mean that they know the language or they have got the meaning like us. So the intrinsic of language model is very different from human model. And you will see in one of the slides that I'll show that the size of them is far below than what is the size of our brain right now. So let's take an example. We think that we are asking LLM my favorite color. So there is no way that LLM understand what is the color concept the way we do. But what it has learned, it has still learned the concept color by understanding the statistical patterns. That the color word, most of the time it comes with red, green, blue, violet, and so many colors of them. So it has learned based on the similarity and dissimilarity. So everything that is happening, it has learned the probability ranking, and then it is doing what is the similarity. So it's a similar concept as any machine learning system has got, that cosine similarity or Euclidean similarity, comparing two vector of words. So this is all based on the number, that red would be represented by a vector, color would be represented by a vector, but then when we compare them, these vectors would have high similarities. And so based on that similarity and the statistical one, it would give the color like red, blue, green, because they happen to appear in the similar space as the vector of color. So that's how this LLM learns. So that's why many times when they become creative, their creativity is very different from the way we are creative. This creativity is very much a statistical creativity. But because as we introduce some randomness, we introduce some noise, so they also learn to generate the sentences. They may not appear in any of the corpuses. And during the training, then it is the system task that make them learn some sensible patterns. So learning is essentially happening unsupervised manner. So for example, they are using this data set called Pi, that is 825 gigabyte, common crawls, 220 billion URL, and then GPT-3 has got 175 billion, GPT-4, we don't really know, but estimated is between 500 billion in this one. So bigger is better, at least for now. But the most important thing, as I said, it generates the probabilities, but it is important to constrain those probability through the training. So the training process in GPT is called instruct GPT. So what happens? We would have question and response, and then we would generate those pair from the web, bootstrap by its own or the humans. Then another way is reinforcement learning. with human feedback to provide the responses, guardrails. So a lot of time, many organizations stop answering in a particular way. So for example, I showed an example last time, give me a joke on women. It would not respond because there is a guardrail not to do it. Ask about a joke on a man, it would do it. And another one is that is becoming very popular these days. It's called constitutional AI. So this is like Universal Declaration of Human Rights. So I'm trained to respond based on what appears in this one. In that way, you teach them what to respond and what not to respond. You are constraining the natural creativity and things like that. But as I said, they are creative, or they seem to be creative, but their creativity is very different from us. It depends upon the corpus that we have trained. It depends upon what we have used as a training one. But because of this training regime, they can do a lot of things. For example, like if you ask, give me a story about snowy mountain, then every time you would get a new story, because they have been trained not to repeat the response. They help with ambiguity. They are trained to do the role playing. So you can do the prompt and say, explain me this information, I'm a teacher. Explain me this information, I am a primary school student or elementary school student. So it would change the response as per playing, because that's how they've been treated. And people have used LLMs to connect two different concepts. For example, we can ask them to relate how quantum computing relating to LLMs. And because of this occurrence and training, they would have find some similarity that they would produce, and they this may be the potential research direction. So this is one way that a lot of academics are using LLM to produce new future research areas. So as I said yesterday, we are really lucky to live in this era where we can rely a lot on these LLMs, but we have to be mindful how we rely onto them and how we want to use them. We can't just completely trust it. It has to come up with the guardrails. So it becomes our responsibility to do that. At this point, we will take a 5 minutes break, and we will join in about 5 minutes. So this is the time to do stretching, standing, take a break, and I'll see you guys at 2:30, 2:40 p.m. or whatever your time is at 5 minutes. Thank you.
पाँच मिनट का ब्रेक है, तो स्ट्रीमिंग रोकूं या फिर अभी चलने दो 5 मिनट के लिए? तो क्योंकि फिर रोकूंगा तो फिर वापस से अलग वो बनेगा, प्लेलिस्ट दूसरी बनेगी, मतलब
ऐसे ऐसे होता है क्या?
अगर एंड कर दूंगा स्ट्रीम तो फिर यही होगा।
फिर जब हम वो करेंगे ना तो एडिट कर देंगे इसको।
हाँ, ये 5 मिनट का तो एडिट हो जाएगा।
Okay, we'll resume the lecture now. So the as we saw yesterday, the building block behind transformer without LLM is actually transformer that changed the game. We could see that RNN RNN was naturally made for the sequence prediction. CNN also was able to learn the dependency. But what made changes with the transformer that it actually allowed to process things in parallel and a few other things. So for example, in transformer, they introduced the concept of positional encoding. So in that way, it allowed to capture the order of sequence. So we exactly know that this is the start of the sentence, this is the middle of the sentence, this is the end of the sentence. So that positional encoding, you will see when Bashar is going to talk about the information extraction, this positional encoding becomes so important. It also became important for the NER task. So we don't have to actually completely rely on the recurrent structure to learn the order. We can learn any type of order. And of course, we all know attention, 2017 very famous paper, attention, that it takes all by the Vaswanis. So it allows to focus on a particular part of the sentence. So we can, if we want to emphasize this is a green apple, but the emphasis on green, we can have this attention and it would response very high probability for that attentive word, and we get it. And this enabled to capture long range dependency and contextual relationship. But what allowed in the transformer architecture was multi-headed attention. So you can actually focus on different part of input sequence simultaneously. So it's not just green apple, it's also apple that we want to focus on and learn the diverse relationship. And the masked attention was another thing that we could process sequentially, sequences autoregressively, and so preventing the information leakage and so on. Then some standard way to forward the process and to allow the backward, that is residual plus layer normalization. So that is kind of like takes care of during the training stabilization, because whoever in this module has learned deep learning model, you would be familiar with stabilize, like how unstabilized the optimization is. Like in module 1, we introduced you to GAN model, and GAN model are known to produce, known to be the most unstable models. So depending upon what architecture and how you are using it, stabilization optimization is always the problem. So the layer normalization worked, and of course the feed forward layer in the end to learn the complex feature relationship and the representation learning. So as I kept saying, that BERT is still the most common model for the representation, and then use those representation learning to do multiple tasks. So all these concepts all together made these transformer like king of AI structure. We know we already had this kind of sequence to sequence model, but they were conceptualized using vanilla RNN that condition on the last hidden state, or attention that condition on all hidden state. But this one heavily relies on the sequential process, making it less efficient for the long sequences. So that's where we got the transformer model, where we have got self-attention. So like instead of recurrence, we have got self-attention and feed-forward, and that can do the parallel processing. So for example, like if we have I like science, it would be decoded to whatever language mujhe science pasand hai, something like that. Then you have got self-attention. How self-attention does, for each encoder position, you compute an attention weight for each encoder position, and then you normalize these weight with the softmax to get a new weighted average. So this allows you to do it for each encoder position in parallel. You are not really backfeeding it. We all know about this. Attention is all you need, and this is the architecture that we have talking about. It has got positional encoding, multi-head attention, then the normalization, then the feed-forward layer. So this is encoder, and it happens n times. So we are multiple blocks, and then a decoder, how it works. This has this input fed, and we have got output embedding similar, but then we have linear and softmax to represent the output probability. So you will see whatever model used for classification or output purpose, you would have this one. So if you are using for fine tuning, usually you froze this part and you would only rely onto the representation embedding that you get from the model. But the good thing, and the one thing I like to emphasize here, is about matrix multiplication. So as we know from the basic linear algebra point of it, matrix multiplication is a very fast processing, and it allows you to do the parallelized computation, different from this sequence to sequence recurrent encoder decoder sequences. Time for the quiz. Yep, the answer is B. As we saw, they are processing in parallel rather than sequentially. So this is some more detail. I may skip it. It's from the Basmani paper, but it gives you the detail about what is the order and what are these ones. So just see an example. So we are able to do the chicken walk, like token and positional encoding, and then answering it as across the road. And this is kind of encoder only and decoder only. So the difference in here is in encoder only, you feed one token to all of the hidden state, to next hidden state, then E2 is fed to the previous and the next, and so on. Whereas in decoder one, you only fed it to the next hidden state. And that's how the masks work. You can mask the attention that you don't want to calculate. So these are the three different types of transformer. Encoder only, that is using only the left part, BERT and its variant. So BERT, and that's why it's originally meant to do the representation. And we all know BERT's bidirectional embedding. So this one gives you all the representation learning. Then we have got this encoder-decoder model, that's T5 and MBART, and then the decoder only, that are GPT and Llama. Another quiz question: why are attention mechanisms critical in transformer-based language models? Yep, the answer is B, because they allow you to focus on relevant parts of the input sequence. So, so now the LLM era, like if you think about the machine learning point of it, when this model BERT was produced, the main purpose was representation. But since GPT and that's where like the Chat GPT happened, they changed the paradigm. So there was a paradigm shift from representation to generation, where they are used in the generation process. So this is little bit more into the detail how this training happening. So you have got input corpus. So this input corpus, so each sentence in the corpus, for example, this one, you represent it into the tokens, labeling it, what kind of token it is, then converting that into the numerical equivalent numbers, and from numerical numbers, it changes into the embedding. So for example, is may appear close to R, or author would appear close to writer. So something like that. So that vector that is created for the embedding, that allows to do the semantic processing. And that semantic processing is very important. And that's how it looks like in the Euclidean disk space, that the vector for author and the vector for writer would be very similar. This would be pump and machine. So something like that. So we call this one as representation, and the embedding. So from this representations, transformer model with billions of parameters learns this kind of predicting the next word. So this is what decoding is doing now, that given the word token, this it would learn is, and so on. And if we have got the reinforcement learning part, that is human feedback. We'll see more into it. I have got some more detail with the GPT model there. So if we put it in terms of LLM, BERT encoder only have got masked language model. So you have got masked self-attention, masked tokens, great for classification, but hard to do generation. Decoder only, they train to predict the next token. They are autoregressive, stable training, faster converging. And then encoder decoder, they have got masked span. So you guys must have heard about Gliner. Gliner is another latest language model really known for NER task. So what it does the masked span. So something like that. You don't have just the next word prediction, but you get the span. So President Franklin, then you would have kind of like another mask, born another mask, January, and then you are trying to predict that span there. So it allows you to learn much better way. So let's look at BERT, but I know Deepak is going to go into some detail as well in terms of how it's used for the classification purposes. So BERT-based model details there. So if we look at this example, and we will see how it does. So if my dog is cute, then you have got CLS token to indicate that's a starting, then the separator. So now you know that there are two sentences. You can use it for whatever task is it in terms of like the pair machine translation, or if it is the following task or the labeling task, and so on. And the masked language modeling would randomly mask. So you got token embedding, you got segment embedding, and you got position embedding. You use these sum of these embeddings, and then your model represents. So you can use these embeddings for many, many purposes, like the classification of a translation and so on. So let's see how BERT is being used. If you have got this sentence pair classification, sentence 1 and sentence 2, then you can add a software classifier on final layer of CLS token, the class label token. And this one then can say whether these the similarity between those pairs. So like Siamese training, something like that. If it's a single sentence classification, that is the most common classification problem. For example, like in Deepak's research, we use it to identify whether a sentence is relevant for that particular prediction task, or we have built a lot of classifier for misogynistic detection or abuse detection. So given a sentence, identify whether it is an abusive sentence or whether it is represent the misogynistic abuse, something like that. So in here you have got single sentence and you have got target. And so again, the same thing, you would add a software classifier on final layer of CLS token. If you want to use BERT for question answering, you have got question and the context. So this one, Bashar would show you how we use this kind of question answering for information retrieval and information extraction. What is my name? And then you give the paragraph where this name appears. So the system learns by the context, and that's where it can explain the what type of question, why type of question, list, find, all kind of question. So in here, we compute a softmax over the dot product of all token embeddings. The most important thing this BERT allows in here, because you have got start, end, and span. So when you so you can have this context length. You can have the context window of 300 words to context window of 700 words. A lot of research, like Dewey, currently Dewey is working on a project for modern slavery identification. So we have used Llama 2, and we have done the experiment with 300 context window to 700 context window. Not necessarily larger window helps, but something in the middle that you have to find optimally. Then BERT is also used for sequence labeling, where you have got the softmax classifier to the tokens in the sequence. Then Deepak is going to show you Roberta and some other BERT models. There are some differences, like Roberta allowing dynamic masking, allowing large batch sizes, and some difference in the encoding, like byte label, byte encoding. Then there is BART, that combines BERT and GPT. So it is doing bidirectional encoder and autoregressive. BART can be very slow to train, but it allows you to do the classification, generation, and translation. Then we have got sentence BERT. Again, sentence BERT is very slow. And we have used it because it uses the Siamese model for the comparison similarity, and cross attention is score that can be very slow. And the most recently, modern BERT, that has been proposed, and what it is saying, that modern BERT is answer to all of the problems that people have been using with BERT. We can see it's a complete tool that is giving us the best speed, at the same time the accuracy. So for example, like a runtime of Roberta, sentence BERT could be very, very high, but this modern BERT could be very slow, but its accuracy is very high as well. We have not used modern BERT in our research, but that's the kind of like the good thing and the irony of this research field as well. Every week you have a new system coming up. You have to be on top of everything, and once the new system comes, you have to adjust our research. So you have to be very careful with that. So that's about the BERT. Now let's look into GPT and a bit of the training strategies, because GPT, surprisingly, offered by yeah, so generative pre-training, like GPT, we know OpenAI, so that is really the proprietary system, but Llama 2, that is Facebook, surprisingly open source. So we will see, and we know more about training of Llama 2. So this is decoder only model, but they are pre-trained and then fine-tuned there. So let's see the training of Llama 2, that is open source and more openly available, more information. So as we know, they are decoder only, so they are autoregressive pre-training, trained to predict the next token with about around 3 trillion token. And let's look at supervised fine-tuning and instruction fine-tuning. So these are the two ways these models have been trained, and then they are further refined using reinforcement learning based on the human feedback, and also some safety guardrails to ensure what is being produced and that the output aligns with human values. Question time. How does BERT differ from GPT in terms of training objective? Just think about it, read once again. I have got some correct answer, but I'll give. Okay, I thought it's a straightforward answer. Now I'm getting the correct answers. Yep, B. So BERT uses the bidirectional, so that's the opposite. The option C, BERT focuses on generating text, where GPT is designed for understanding task only. That's not true. BERT and GPT use the same training objective but differ in architecture. They differ in architecture, but they also have different objectives. Remember, GPT has got the next word prediction, and that's why it's a decoder model. So it has got this softmax function that is embedded in its architecture, whereas BERT originally has been built for representation tasks. So that uses mass language model that learns the representation of the language. So answer is B. So now let's look into supervised fine-tuning very quickly into that. So as we know, GPT, it's made for autoregressive prediction tasks. So what it does, loss is computed only for target tokens. So you have target tokens, and during pre-training, all tokens are targets. So every next word is the token prediction for the preceding sequence. Just think about the complexity. We are talking about so trillion, and that's why we say they spent millions of dollars building this model. So at our scale, nobody really should try to even attempt to build this language models. We should focus on how we can use them. And then they have got input and target. So they have got instructions plus input as input with the target in SFT, and only input as input with shifted input as target. So they have got this predefined input and output. And what they try to do, they are trying to improve the generalization. So during this instruction that is given with the input, you teach it that how this answer should be produced. But a lot of time, we don't have this supervised data or enough large data. So how they have done, they have used this LoRa low rank adaptation there. And so that's how instruction tuning looks like. You talk about, here is a goal, get a cool sleep on summer days. And then it would say, how would you accomplish this goal? Keep a stack of pillowcases in fridge or in oven. And then you will give it the answer, that this is the correct answer. And you will also give in, like if it's a translation problem, then you will give this machine translation and so on. So lots of varieties of these instruction given with the input data that is part of corpus. And then they are trained to this responses there. And it is kind of mimicking the human reasoning, that and to trained, it is not possible. Because earlier when these models come, usually they are not produced and not trained to say no. Or like if we think about grounded, what is grounded in machine learning? If you have got cat and dog classification problem, you only classify to cat and dog. You don't classify to anything else. Generation kind of helps you, but still it's a limited. And then a lot of time it does the unsafe output. So you have got then the last loop where you do the human alignment, that no, this should not be done. So in last module that Joy would introduce, she is going to talk about some systems where we developed using the guardrail. So this particular output should not be produced because it does not align with the organization's motto, something like that. So you give lots and lots example, and that's how those language models are built. Yep, I think this question we have got undivided attention or no conflict here. So the answer is B. They do have generalization, they can process sequential data, and they can learn the long service dependency, but they are known for high computational cost and memory requirement. So just something like that. That's how they have been trained, reinforcement learning. So here you have got next token prediction. So you have got the decoder model, you have got the softmax function on the top of the feed forward layer, and that generates the probability. And at the same time, then you have got reward model structure. So you have got this loss function using the regression layer, that the answer by this probability, and if it agrees to the human notation, then you score the higher value, otherwise you say no. So in the early days, like if you notice, when ChatGPT was proposed, it was really of high quality. But once it was made available, and in the beginning, when people were using it, ChatGPT constantly started to use that data as human feedback. And because it was open to all, it actually diluted the quality of the data there, and its quality was really degraded, and then they controlled it, how it's used. So if we are using all these human alignment, reinforcement building, so does it mean that LLM will never produce harmful output? No. You cannot be exclusive with LLMs, because we are talking about so many unseen scenarios. There is no way we can be exhaustive here. So the concerns are that how it happens in the security, people have started to do adversarial attacks, purposely infiltrating their data there. So for example, like we have done some experiments in our research group, and we found that Claude can produce harmful output the least when compared to ChatGPT and Llama. So then how do we inferencing? The prompting, I would not go into much more detail, but we have seen, and we would see in some other modules as well, chain of thought, instruction fine-tuning, multitask fine-tuning. So essentially what we are trying to do, we are doing the prompting and instruction tuning to make it better. So, these are the examples there. And also then fine tuning that we do, it creates the specialized models. So how this fine tuning works, you have got a pre-trained model that is on generic data. The way you learn the knowledge gained by this model, by freezing some weights, adding some more layers, depending upon what is your task, whether it is domain specific or task specific, it allows to do it. So essentially what it does, let's say you have pre-trained a language model, and you want to use it for some classification task. So what you would do, you would use, so this is your corpus, maybe a small scale label data, that this story is about sport, this story is not about sport. And then you would freeze some of the layers of these pre-trained language model at some, depending upon what model you are using, what task it is, you would add something on top of that. And this is called fine tuning. And now you have got the model. So this model you would be calling it as your machine learning model. So for example, in this case, that's how we have used hate speech. So we have got input data that this tweet is a hate, this tweet is not a hate. We use BERT model, freeze, add some layers. We have got now the classifier that says this tweet has got 20% possibility not to be hate, but 80% possibility to be hate, something like that. So fine tuning can be done on many tasks. You have got the foundational model that is trained with large corpus. Now you have some supervised with the small data sets, and you do use it for question answering, sentiment analysis, and ER. So it would all depend upon what model you are using. So it would dictate what kind of freezing you are doing, or what kind of layer you are adding. But your data, if it's a question answering, you would have some subset of these, the same for other one. You can also fine tune for domains. So you can make your large model. You don't necessarily have to use it, but you only use it customized for your information. So like for find any domain like finance, legal, and so on. So Deepak is going to show you some of the examples of task-specific adaptation. Okay, so main goal of fine tuning is to adopt the pre-trained model to specific downstream. So yes, almost everyone is getting it correct. Answer is B. So that's why these systems are called general purpose monolithic model. You can do question answering, sentiment, label, or information extraction, topic modeling, some guardrailing, and so on. Okay, another question. How do large-scale pre-trained language models like GPT-3 enable zero-shot learning for downstream tasks? So I think it's a GPT-3. Yep. So like GPT-3 model would do it the second time. If you have got BERT kind of model, then you might need task-specific head. So now the question is like, what kind of training or the tuning that you need to make your model customized for your own need. So fine tuning, that gives you the strongest performance, but still it requires a large amount of annotated data. And it may risk poor generalization or spurious feature exploitation. Another one that you use to use LLMs for general purpose task is few shot. So much less tasks, so you don't really need too much task-specific data, not really too much of feature exploitation, but it's a challenging. And then one shot, it's the most natural, giving the human instruction, and zero shot is most convenient. So you can see the convenience grows from top to down, but the stronger performance happens when you go from bottom to top. So you need to find a trade-off that you are looking for when you are using these LLMs. Now we are going towards the wrapping up the module. So as we have seen, we saw early models, n-gram models, and Markov models. But it was important to learn the basics of these systems. As we saw, n-gram model, they are simple and effective, but they are limited. Markov model, they learn the sequences, but they struggle for the large language dependency. Then the deep learning era came in, and we got much better language models, RNNs, LSTM, CNN, and then came transformer. And it changed the world really with the self-attention mechanism, and they became the block for LLMs. So we can see that then all the language models like BERT, GPT-3, PaLM, BART, they start to appearing in. And then came these LLMs, encoder only, BERT, Roberta, Electra. BERT is actually known for bidirectional encoding. Then we got decoder only, GPT. They are very good for ones. We got encoder decoder, T5, BART, very hard to train and expensive. And the current trains that we got is multimodal models and the continuing learning, that especially how can we deal with the catastrophic forgetting there, because how can we adopt them for the overlong. So continuing learning and multimodal models. So multimodal LLMs, they're essentially not just the text, but we have got images, we have got audio, we have got some tabular data. So like Gemini from pre-training, Audio GPT Flamingo from instruction training, and then Clip, that is from the continuous embedding, where text input is concatenated with the image and pre-trained independently. So if we look at the language model progression, we can see as we are evolving, we can see these language model can deal with large number of words. They can, and it's a proportionate. The larger size they are, the more pricier they are becoming, at least at the time of their creation. But the left-hand side slides that I got, I really found very interesting. That compares the size of these models against the size of the living being brain. So like GPT-1 is about the same size as ant brain. GPT-3 and T5, they are about rat brain. And all these models are far away from human brain. But again, they are catching up. And that's where we would have many more discoveries and the resolution there. that would happen. So it's important that you choose the right LLM model. There is no perfect model. Trade-offs are required, like maybe because of the architecture, because of the data they used, because of the way they have been trained. So as an organization or as an individual, you would be thinking about privacy, quality, cost, latency. So these are some of the factors that would dictate you to decide a particular LLM model. And that kind of like leads us to another topic: how do we evaluate LLM? The output that we got from LLM, how can we say it is correct and not? And that's where in the module with Stephen, we are going to introduce LLM as evaluator. We use them to see how good they are. So many researchers are comparing the results and producing, but it's still far from finding any conclusive remark to say this particular LLM is good for this particular task. There is not really a single consensus. Um, um, and to kind of like wrap up, they still struggle with the bias problem based on the data they have been trained on, the training, because training is still, instructions are part of the training. So it's a very much human generated training. They lack common sense. I spent a bit of time to explain that their way of understanding and meaning is very different from the real world, the way that we see. So how can we make them more common sense? And we all know that they have difficulty performing some complex reasoning tasks. They can do some simple tasks like rewriting, summarizing, question answer, that the pre-deep learning era. So if you think about it, that in the like I have been doing information retrieval even in 2000 or 2010s. So the tasks that were done at a small scale by those probabilistic models, most of the time those tasks are achieved by these models because their fundamental is still based on the model. Those were the pre-deep learning era. So they are still struggling to really understand some abstract concepts. So we really need to have some groundbreaking research in terms of how we can train not just the next level different. So future development, of course, the new capabilities, multimodal, multilingual, more complex reasoning that actually aligns more of the human thinking. Performance-wise, we needed to hallucination, reduction, alignment with human, complex reasoning task. A very simple is that most of us, we struggle, how can we increase the context length? Like still they are limited to about 700 when it goes to the research purpose, especially when we are using some data lakes and so on. Otherwise, context length window is really small. Improve the training model structure and so on. Efficiency, they can do hopefully the architectures, the new architectures like GPU, TPU, HPU, or even the quantum computing may make them more efficient. Then we have concern in terms of safety. How can we mitigate the bias, reduce the harm? Adversarial robustness, like this talk, this course is not really meant so much for adversarial robustness. We only include bit of the safety from the guardrail perspective. And the last point is interpretability. How do we know that what they do, how they do it? So decision making, why is it happening? And the last point is, of course, the alignment. So to summarize, they are large-scale model that possess astounding ability, the NLP. The scaling that we have seen from GPT-1 or BERT to Modern BERT or to GPT-4 and Llama, that is really impressive. And that has led to many tasks and many new abilities. If we look at all the architecture, decoder-only architectures are popular. And as I kept saying, that the more complex architecture is, more complex training or the instability and all kind of training problems are. And so that's why decoder only. But what it means that decoder only, it goes to the 30 years back foundational concept of language modeling, language next level prediction. So can we think about something really innovative that becomes the foundation of the training data? And then they are usually pre-training, self-supervised reinforcement that makes them trained to learn general purpose tasks. And then there is many evaluation like ICT and COT. And recently, multi-model LLMs really have become popular. Same, I would like to acknowledge the team members of my group that are part of this course, but then the wider research members as well, the industry people, interactions of my colleague, and the execution of those projects led to creation of this module. So thank you very much. And this is just a bit of my detail, and I look forward to talk to you in the next following sessions. So now we will have a break for about 45 minutes, or and then we will see. So I'll stop sharing my screen.
Yeah.
And I'll hand over to Namita.
Yeah.
Professor
Thank
Namita.
you.
Thank you.
Thank you, Dr. G, for sharing your valuable insights on generative AI and more than that, all the transformers. So some of the participants are joining first time this course, means they are new, and some of them are having the experience already working in this area. So you have covered from all the aspects, that is very nice. And the questions are really very helping. They are very helping to be attentive for the class. And as we are maintaining the WebEx attendance and sharing the materials on Canvas, people are using it widely. And YouTube link is also shared amongst the participants. Those are not joined, but somehow they are using it. Like my friend, Dr. Aditi Shran from JNU, she is watching it and she is appreciating it. And thank you very much for, we'll be back on at 12:15 Indian time, right? Thank you so much.
45 minutes, and Deepak is going to run the workshop, and I hope you will find those sessions very useful as well, because I think all my team members have really worked hard to produce these codes to relate to these advanced concepts.
Yes,
thank you.
That's true. Thank you. Thanks a lot. And we'll be back by at what time Deepak will join us?
In about 45 minutes.
Okay. So
isn't it?
Yeah. So 11:45 will be there. 11:45. Sorry, 12:45. Got it. It's 11.
So right now, like,
11:45.
And it is 3:30.
So all the participants are requested to please come back at 11:45 Indian time. Is it okay? You can write on chat. We are here to see that.
So, Namita, what is your time right now? 11 a.m.?
Yes, 11 a.m.
Yeah. So, so you are saying 11:45?
Yes.
Yeah, in 45 minutes. Yeah. See you then. Yeah.
Thank you so much.
See you guys.